Well, I'll get started. Let me begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class and this time we have to study your creation. Help us to glorify you, Lord, in what we do, Lord. In your name I pray, Lord Jesus. Amen. So, first order of business, I thought I should take a second to make sure we're all on the same page about like how to do some basic calculations. So, in particular, I just want to talk about orthogonal complement. In the context of Rn. All right, so this is kind of the old news for some of you, but for others of you, you didn't take my 221 course, so you might not know this stuff. Maybe you've rediscovered it for yourself, I don't know. But let's work it out together, because it'll help us make more sense of a proof I go over in a bit. All right, so if we have S, and let's suppose it has S1, S2, k-fold vectors, all right? This is a subset of Rn. And I want to calculate, let's say, the perp to that, right? What is the perp to S? Well, it is by definition x in Rn such that what? Such that x dot, I'm going to write it the other way. I'm going to write it as S sub j dot x is equal to 0, right? For j equals 1, 2, all the way out to k, right? So let me rewrite this again. X is an element of the perp of S. Means that you have to have S1 dot x equals to 0, S2 dot x equals to 0, all the way down to sk dot x equals to 0, right? But this is the same as like S1 transpose x equals to 0, S2 transpose x equals to 0, sk transpose x equals to 0, where S1 through sk transpose are row vectors, right? They're row vectors, which means you can trade this for simply the statement that the matrix S1 transpose, S2 transpose, sk transpose times x is equal to 0, which is equivalent to saying that the matrix S1, S2, sk with the transpose times x is equal to 0. Now, traditionally, we call that matrix the S matrix, right? Like this, in our traditional usual notation, this is the S matrix. So we've got S transpose times x is equal to 0. All right? So what's all this mean? This simply means that this is true if and only if x is an element of the null space of the transpose of the S matrix. So, so there you go. And that is pretty straightforward how to calculate it, right? Like example 1, if I wanted to find a basis for like S, suppose S is equal to, I don't know, 1, 1, 1, 0, 0, 1, 1, 2, let's say. To find S perp, I'm looking for the null space of the matrix 1, 1, 1, 0, 0, 1, 1, 2, right? And of course then I can just do, row operations. That's the same as the null space of 1, 1, 1, 0, 0, 0, 0, well, 2. which means what? We've got what, like x1 plus x2 plus x3 equals to 0, and 2x4 equals to 0. So we're looking at the span of, like minus x2 minus x3, x2, x3, 0. So minus 1, 1, 0, 0, minus 1, 0, 1, 0, which you could have guessed. It should not be lost in this discussion that if you can see, by looking at the matrix that you're given, by looking at the vectors which you're given, right? Look at these. Can you find vectors which are perpendicular to both of these? Isn't it obvious that, oh, wait a minute. Rats, I did something wrong. What have I done? I must have miscalculated something here. Ooh, uh-oh.
Then you go from S-perp to null on the second.
Oh, yeah, this is totally bogus, right? I have to do the other way. Oh no, I need to teach 221 again. I've forgotten how to row reduce. That's not good. Let's try this again. How about 1, 1, 2, and yeah, this is so embarrassing. Oh no. Oh well. I guess, well anyway, but you can check you should check your answers, right? Which is what I was just doing. The dot product of this with that is 0, but the dot product of this with that is 1, which is not 0. So sorry about that. Let me fix this. So apparently, the equations I should have used, x1 is 2x4, and x2 is minus x3 minus 2x4. So my typical, so I'm looking at the span of like, 2, minus 2, 0, 1, and 0, minus 1, 1, 0, I think. Now we can check the dot product. 0, very good. And this one, I got a minus 2 plus a 2, 0, cool. That, 0, yep, we're good. So this is the calculational method to find the orthogonal complement for a subset of Euclidean space, right? Now, if we're in the context of inner product space, we just have to work it out, right? There may not be a method like this. I mean, you might still be able to essentially do this if you work through it, but I don't know, I haven't tried to provide you quick calculational methods in the other context. They're probably there to be found. I just haven't derived them at the moment, So application of this, what's the perp to the column space of A? Remember, we have this result that the span of S perp is equal to S perp. So if you take, you could just look at the columns of A, right? That's a generating set for A, for the column space, right? Because the perp generates the span, you don't need it. But applying this result, we just worked out, what is this? This is the null space of A, almost A transpose, right? So the perp to the column space is the null space of the transpose. That's really simple. It's really quite beautiful how that works. And so what does that mean in terms of like left-to-left multiplication map? So the range of the left multiplication by A map, right? The perp to that is the null space, or the kernel if you like, of the left multiplication by the transpose map. But anyway, so yeah. So that's one thing I wanted to share with you. Another small thing I wanted to share with you is just like a point of a slightly abstract point, which is that any finite dimensional vector space that we look at, we can always build an inner product on it. This may be a homework problem I assigned. I either assigned it and then unassigned it, or I actually assigned and I'm working one of your problems for you. Either way, I'm fine, okay? But think about this. If we have, the dimension of V is equal to n, and like beta is V1, V2, Vn over F, right? Then we could define an inner product. Check it out. Here's how we do it. The inner product of x and y. So we're looking at the inner product of the sum over I of x sub I, v sub I, sum over j of y sub j, v sub j. Well, you know what you can do? You can just pull those sums out and pull the constants out as appropriate, y bar j. All right? And you notice then, if we assume, so what I'm doing by writing that formula down is I'm building in the additivity and the conjugate linearity of the second spot by writing those formulas. This is like the idea of linear extension extended to inner products is what I'm doing. Okay? And if I define then the inner product on the basis, then I should define the inner product. So what should you, what would be the nicest thing you could do here? How about Kronecker delta ij, right? If you do that, then the formula is simply the sum over, I, 1 to n of x sub I, y bar I. So you could do this. You could just define an inner product relative to your basis to make the basis orthonormal. Nothing's stopping you from doing this, but it's completely divorced from the natural geometry of your example. All right? So if I do this for a basis which is not orthonormal over one of the examples we have, we get some kind of wacky geometry which is not in any nice way related to the actual geometry that's natural to our examples. Right? So anyway, just a passing comment. We can always make any finite dimensional vector space into an inner product space. More than that, we can force orthonormality on the basis by this construction. It's a very silly construction, but there it is. Yeah. All right, now that I got that out of my system, I need to show you guys some stuff. Because I have managed to make things like way more complicated than they actually are in the last day or two of class. And so let us just, oh no, oh, this is bad. At least I brought my phone. Stupid two-step verification. Yes, it's me. Let me be. All right. Me making mistakes is hilarious. I heard that. Bad people. Very bad people. All right. I guess I probably should plug this thing in, huh? So I still owe you guys the bonus project that I promised. I haven't gotten that put together yet, but I will in, yes, a second bonus project. So All right. So we are going to travel back in time to the time before we defined the adjoint. We're going to develop the theory of the joint from scratch. I have all of the arguments here in their entirety, and we will look at them together. And we're going to go kind of fast because we have been through these before, but yeah. And I will post these for you guys. So let's just start at the beginning. It's a very good place to start. Theorem 6.8, via finite dimensional vector space, inner product space over a field F, let alpha be a dual vector, then there exists a unique y in V such that alpha of x is xy. First of all, point of order, I mentioned this sharp and flat map. I've given up on that for this semester, so feel free to ignore what I said about sharp and flat. I will bring that back for advanced calculus for those of you who come there. So the musical morphisms, they are, at least until for now, they're out, unless I can fix some things. But there's some fundamental issues about conventions that I haven't quite come to terms with yet. The book that I like the most, which does the musical morphisms, sadly has defined the inner product with the roles of the first and second slots of the inner product exactly backwards, so that they assume conjugate linearity in the first slot, but regular linearity in the second slot. Apparently some books do this. It leads to slightly different formulas, and it's very disconcerting if you're not aware of it. So I haven't, anyway, focus. So we let y be the conjugate of the value of the dual vector at vi times vi like this. That's how we build the vector y. We plug it in. We define h like so and do the calculation. We did this decently. And that gives us that h is equal to alpha because it agrees on a basis, right? If we have two linear transformations are equal on a basis, then they're the same transformation. And if we had another choice for y, say y prime, then you would have xy is equal to xy prime for all x, but then by the cancellation property for the inner product, that implies y equals y prime. So there's your uniqueness. Now, so that leads us to the existence of the adjoint theorem, which is here. Oh man. I'll get it eventually, folks. Slightly downsized. So given a linear transformation on a finite dimensional inner product space, there exists this unique T star linear transformation which satisfies this lovely identity where you can shift T of x to T star of y like this, all right? And so we let y be in V. We define a dual vector as such. We prove that it in fact is a dual vector. Here's the proof of linearity. And we did this successfully in class. That was fine. All right, so there exists a unique y prime in V such that alpha x equals to y prime by the previous theorem. And hence T of x y equal to xy prime is equal to x T star y, provided we define T star y as y prime. That's a good definition because this is a single thing. We'd like for a function to be single valued, so T star is a function. That's great, but is it linear? Well, linearity is then given by this calculation down here. If we have y1 and y2 in the vector space and see a constant, then for any x and v, we can do this calculation. Basically, the game that's played here is we use the defining characteristic of the adjoint to move the star back to the first thing. And as such, then we can use the conjugate linearity of the inner product, right? Sometimes called the sesquilinearity, like 1.5 linearity. Pull out the complex conjugate, break up the sum, and then we shift the t back to get the t stars again, and then use again the conjugate linearity of the inner product to bring the c back in as a the conjugate goes away when we shift it back there. And lo and behold, since this holds for all x, again by the cancellation property, it follows that t star of the linear combination is the linear combination of the t stars. Hence the adjoint, as it's so called, is linear. And then to get uniqueness, if we have another operator u that satisfies the same defining condition for the adjoint, then that again would give us that equality for all x and y, which again implies that it's the same operator. So the adjoint of a linear operator exists, and it is defined by that defining property. And this is a little bit it's a little bit unsatisfying as a student for this to be the definition, right? Because You like for it to have a formula, you know? It's nice to have a formula for the adjoint, but we're defining the adjoint in kind of an implicit way, right? We're defining the adjoint as being the operator that satisfies this equation. So I don't have T adjoint equals something as a general formula. Although, given a basis, we can define it in that way, as we'll see next. But there it is. So this is the adjoint. It is, again, a linear transformation on V. Now, so in the infinite dimensional case, we still call it an adjoint. However, we're not guaranteed the existence. There do exist infinite dimensional linear transformations where the adjoint doesn't exist. All right. Then there are some that do, as we'll see. There, I have an example a little bit. Proposition. And so this right here is one of the things that confused us, because we should have done this. If we had done this here at this point in our logic, everything else would have fallen into place. All right? This was the missing link in our logic. This thing right here is so simple. What's that? We did it, but we did it in the midst of other things, and we didn't emphasize its importance. And like basically, we're going to note this is true and keep doing it. You know, the abstraction of the idea is what we're missing, I think. Maybe it was just me though. You guys might have understood. You know, so anyway, so here we go. This, of course, is equal to the complex conjugate of flipping the order. But if we flip the order, we can move the T to the other side by the definition of the adjoint, like such. But then, of course, to flip it back, we complex conjugate again. And then, of course, those cancel, right? Because the complex conjugate is nothing. And so we get x T of y is equal to T star x of y, which is what we were setting out to prove. So we can move the star to the left or to the right. All right, moving an operator in the finite dimensional context either from one side or to the other of the inner product adds a star. It's simply that. That's like the way to remember this. And this actually gives you a method for calculating the adjoint in terms of coordinates. In terms of coordinates, if you have an orthonormal basis, that's the fine print here, orthonormal basis, then the matrix of the adjoint is the so-called adjoint of the matrix. So this we defined earlier to be the conjugate transpose. So we take the complex conjugate of the matrix and then we transpose it. And that's what you see down here. So this is equal to that, but if I move it, so flip this, flip the order, I've got complex conjugate of VI with that, but then move the T star over there. Well, this is exactly the Jith component of the T beta beta matrix. So that is the ijth component of the conjugate transpose of that matrix, which is what we were trying to prove. This is also very important. We must remember this. The adjoint, the matrix of the adjoint is the adjoint of the matrix. And I said it has to be orthonormal basis, but you know, guys, oh yes, it does, because remember, in order for this equation to calculate the components of the transformation, the matrix of the transformation, that's where the orthonormality is used, right? Generally, how would you calculate the ijth component of the matrix of a linear transformation with respect to a basis? Well, you'd have to sort through the coordinate maps and all that, right? But in the case of orthonormal bases, we can just use the inner product to calculate the components of the matrix with respect to the basis. That's a great logical savings. That's part of what makes this chapter so much easier in some sense than the others. A corollary is that the left multiplication by the adjoint of the matrix is the adjoint of the left multiplication map. This is very easy to see from what we just did above. And then we had these properties, which I was a little bit befuddled on how to prove some of these. But if we have two linear transformations, and we're talking about their adjoints T star and U star, then the sum of the transformations, well, the adjoint of the sum is the sum of the adjoints. The adjoint of a scalar multiple is the conjugate scalar times the adjoint. Sachs-Schuh's principles at play, so like TU adjoint is U adjoint, T adjoint. Adjoint is back where you started. The adjoint of the identity is the identity. The proof of all of these are good like, thank you for giving me that on the test question. Like every one of these is a decent test question, right? Like they really just meaningfully use the definition of a joint and the properties of the inner product, every one of them. So like definition of t plus u is t of x plus u of x, which then by definition, by like axiom 1 of the inner product, I can break up the sum. Then I shift the operator over to the other and make it the adjoint by the definition of a joint. These exist because they're given to exist. This isn't even finite dimensional. This is possibly infinite dimensional, this theorem. We're just assuming the existence of the adjoints. So assuming the existence is what powers these calculations. But they're given to exist, so there it goes. And then, by definition, the inner product is additive in the second component, so I just take the sum and bring it inside the inner product. But then definition of the sum of two maps is this. And as such, we've shown that this map of x comma y is equal to x comma this of y. That makes this the adjoint of t plus u. Therefore, the adjoint of t plus u is the adjoint of t plus the adjoint of u. And the logic for all of these are pretty much just the same. Like the next one here. If I have tu of x, that is t of u x of y by definition of composition, right? Which then, if I shift the t over here, I get a t star. So I get u of x, t star of y. But then, by definition of adjoint, I get u adjoint, t adjoint of y when I shift the u over. But you see the t has to come first because it's on the outside. And then I've got x with this thing, but x with anything over here acting on y, whatever that anything is, must be the adjoint of tu. So tu adjoint is u adjoint t adjoint. Yay! And there it is. And I'll also do part D. I don't think I did all of them, but here's D. T adjoint y is equal to x. So this is our lemma from before, right? That implies that if I move t adjoint to the other side, that would be t adjoint adjoint, whatever's here. So that makes this t equal to t adjoint adjoint. So t adjoint adjoint is equal to t. I just could not see that other class. I could not see it for the life of me. Now, a corollary to this is we have the same results for matrices. Of course, all of these, we could take it as a corollary to the theorem above, or we could just straight calculate these from matrix algebra. Like the transpose of the transpose is back where we started. If you complex conjugate, the complex conjugate, you back where you started. And if you just use those properties, it's easy to derive all of these from that, right? Or you could view it as a corollary to the theorem as the textbook does, yeah? So moving along here. So if you look at the exercises extend the notion of a joint to the possibility that you have a linear transformation that goes from vector space V to vector space W. So far, we've only talked about the adjoint being based for a vector space to itself. And we're going to stick with that focus, but I'm just going to leave it to the exercises for the moment. But this is kind of that world, because here you notice that we've got a rectangular matrix possibly. So we're not dealing with the same inner product on both sides. Notice that this is the m-dimensional one, this is the n-dimensional, as in mommy and nanu. And so yeah, if you do that, well, here's the proof. Like the formula for the complex inner product is simply the conjugate transpose of the second thing times the first thing, which you can conjugate transpose that if you just use your imagination, they're both there, right? And then sock shoes gives you this, which gives you that, which gives you this. So it's just a calculation that you can shift the matrix from one entry to the adjoint acting on the other entry. In the context of a real vector space, the way this looks is that if you have a matrix acting here, you can move it to the other side and have a transpose. This is just always true. Whether the matrix is symmetric, anti-symmetric, whatever. This is just a general identity for matrix calculation. So yeah. And here's how that calculation looks if you just use the adjoint properties. So I have AXY with M, which is Y adjoint AX. That's the formula for the complex inner product, and or possibly real. If it's real, the star becomes a transpose is all. And so that's A is conjugate conjugate, right? But then Sachs-Schur's gives me that's A times Y conjugate, which then is that. So it's even a little bit easier if you use the conjugate notation. This proof and that proof are equivalent. They're just a different notation. This right here is a little bit interesting. Lemma 2. The rank of A conjugate A, they say conjugate, I mean what's the name of this stupid thing? The rank of the adjoint of A times A is equal to the rank of A. This is kind of an interesting result. So let me walk through it. A is m by n, and the adjoint of A is n by m. So if we look at A adjoint A, it's n by m times m by n, which is n by n, right? So both A and A star A, they're both matrices with n columns. Okay? They're both matrices with n columns. Thus, the rank, the n is equal to the rank of A plus the nullity of A. But it's also equal to the rank of A star A plus the nullity of A star A. Therefore, in order to get the rank of these being equal, we simply need that the nullity is equal. We can measure that by showing actually that the null space of A is equal to the null space of A star A. I mean, it doesn't have to work out that way, but it happens to work out that way. And since that's the case, that will suffice to prove the claim. So what we do then is if x is in null A, that means AX is equal to 0, which means that A star AX is equal to 0. So that was easy. Null space of A is a subset of the null space of, oh man. Oh, that's null. I was looking at that like a NU or something, but anyway. Okay, so if x is in the null space of A star A, that means A star AX is equal to 0, right? But then, check this out. If we do 0 is equal to that, right? Because 0 with anything is inner product of 0. Then we can shift one of those A's over to the other side. But then, why do I have two? I mean, I guess I can. What's that?
Because you shifted.
Oh, because I shifted it. Yeah, thank you. I'll get with it eventually. So we get AX is m, but that's equal to 0. The only way you can have the inner product of a vector with itself being 0 is if it is the 0 vector. Therefore, AX is equal to 0. That shows x is in the null space of A. Therefore, we've shown double containment. They're equal. Therefore, their nullities are equal. Their dimensions are equal. Consequently, the rank of the two matrices are equal. Hooray. So that's kind of cool. Now, you might wonder why on earth we're doing this. And that would be a fair question. The answer is to solve the least squares problem. All right. So like, in the way I usually the way I usually explain the least squares problem is the problem is how do you solve an equation which isn't consistent, right? If you're trying to solve AX equals to B and B is not in the column space of A, well, you can't solve it, right? But you can try to find the best approximation. And so here's kind of a picture. If you imagine the plane being the column space of A, which is the range of LA, then we're trying to find the point which minimizes the distance from Y to the column space. That would be the best, the best approximation to the inconsistent system. So the theorem basically is that there exists a unique AX naught in W, which is closest to Y. That's the closest vector property. We prove that another day. All right. The question is, how do we actually calculate that? All right. So that's what I'm showing you right now. The way to calculate it is as follows. So we're trying to minimize this error, which is the norm of AX minus Y. The Y is given. So that means we want Y minus AX naught to be in the perp to the column space. And so that means that AX with this has to be equal to 0. But if we bring x over there, we get A star A times x minus Y equal to 0, which then implies that A star times AX naught minus Y equal to 0, which is to say that A star AX has to equal to A star Y. So these are usually called the normal equations. The solution to the normal equations gives you the best approximation. And if you tilt your head and squint, you can kind of see what I started class with behind the scenes here. But it's not direct. If I remember, I'll make an announcement later where I share with you in my 221 notes the calculation which leads to the normal equations, because there it's done in the real context. That might be helpful to some of you, I don't know. But anyway, if the rank of A is n, then the inverse of A star A exists, right? Because that's an n by n matrix with rank n, it's invertible. And so you can straight up solve for x naught as equal to the inverse of this matrix times A star and the given y. That's the best approximation to the inconsistent system AX equal to y. That's the theorem, which is just the least squares method in summary. So in short, if you want to solve the least squares problem, you need to solve the normal equation. What's new for me, though, is there's more we can do. We can talk about the solutions of minimal norm. And so here's the next. So a solution is a minimal solution if it solves this and it's the smallest solution possible, all right? To put it in more geometric terms, the minimal solution is the solution of AX equals to B, which is closest to the origin. So if your system happens to allow x equal to 0, that's your minimal solution, game over, end of story, right? But if B is non-zero, right, you might not be able to, well, you're definitely not able to put 0 as the solution, right? If B is not equal to 0, 0 is not a solution, right? We can all agree, I hope. So here's the method. Well, the theorem anyway. If AX equal to B is consistent, so that means B is in the column space of A, then there exists exactly one minimal solution S of AX equal to B. And S is an element of the range of the left multiplication by the adjoint of A, also known as the column space of the adjoint of A. And the vector S is actually the only solution to AX equals to B that lies in the range of the adjoint, left multiplication by the adjoint. In fact, if U satisfies AA star U equal to B, then S is equal to A star U. So I'm not particularly interested in the proof of this theorem, so I'm going to skip past it, but it's pretty straightforward what I'm skipping. I really want to show you the example. That's kind of probably more interesting to you guys. So check this out. Suppose you're trying to solve this system of equations x minus y plus z equal to 1, x minus y plus 2z equal to 2, x minus y plus 3z equals to 3. This is a consistent system. You can check that the solution set is 0, 0, 1 plus the span of these guys. All right, so it actually has a one-dimensional null space. If you calculate AA star, which in this case is just AA transpose, you get this really cool matrix 3, 4, 5, 4, 6, 8, 5, 8, 11. And calculation, which I'm not going to show, shows you that the reduced echelon form of this matrix actually works out to such. All right? So the normal equations have this as a solution. All right? And so the like general solution to the normal equation, well, there's infinitely many of them, right? Because this is this matrix doesn't have rank 3. The rank of the matrix was 2. It's not invertible. All right, so we're outside that context, but there is a whole line of solutions, right? And you're like, wait a minute, I thought you said there was a unique minimal solution. Well, hold on a second. What happens when we feed this u into the adjoint? Like multiply u times the adjoint. All of the variability, it cancels out, and you're left with a single solution, 0, 0, 1. So the solution to the system which is closest to the origin is 0, 0, 1. This allows us to find the solution closest to the origin of a non-homogeneous problem. That's pretty nice, because those problems in Calculus 3 are kind of horrible. And if you go back and look at the problem, this is totally unsurprising, right? If you think about this, it's a line with base point 0, 0, 1, and the direction is 1, 1, 0. Of course, the closest point to the origin is the base point, because the direction vector to the line is sort of perpendicular to the base point. If the base point was not perpendicular to the span, then it would be more interesting, the calculation. But it would also be more of a pain for me to work out, so I stand by my example. There is a completely different example in the textbook, all right? So I added something here. Woohoo! Next. 6.4. So 6.4, we did this calculation last class. We showed that If T is an eigenvector, then the adjoint also has an eigenvector. And the way we did that was we supposed TV is equal to lambda V. So that gives us 0 with X is this. But moving it to the other side gives us the adjoint using the properties of the adjoint, which again, using the properties of the adjoint gives me that, which shows you that V is perpendicular to this for all X, which is to say that V is in the perp to the range, which means that the range isn't everything because there's something in its perp. So therefore, the range is not all of V, which means that this mapping is not onto. But since we're talking about a mapping from V to V, that means that the kernel is non-zero, hence there exists a vector in the kernel, and that vector in the kernel is exactly the eigenvector which we sought, W. So T star minus lambda bar W equal to 0, which is to say that lambda bar is an eigenvalue with eigenvector W for the adjoint. And that was the first thing. We proved this last class. Moving on. A polynomial is split if it factors into a product of linear factors. There's a theorem by Schur which says that if you have a linear transformation on a finite dimensional inner product space and the characteristic polynomial splits, then there exists an orthonormal basis gamma such that the matrix with respect to this orthonormal basis is upper triangular. Now, the proof of Schur's theorem in the book is, it is like a half a dozen homework problems. It's like every sentence is like, see exercise such and so forth from section such and so forth. It's like, oh, well, if I had planned ahead to have you guys work all of those homework problems, this would be great, but I didn't. And I don't want to like just dump them on you now because they're all kind of hard. So I don't really like the proof in the I don't like the proof in the text that much because it assumes many things we have not done. All right, and it's based on the weave, and as you know, you have to be very intelligent to do the weave, and I'm not sure we're ready for that. So I'm sorry. That was a very, very complicated Donald Trump joke, if you're wondering. In his recent interview, 3-hour interview with Joe Rogan, about 2 hours in, he talks about doing the weave. If you haven't seen it yet, it's hilarious. So, also warning, adult language. It's Joe Rogan, right? Anyway, so I come up with a proof for the Schur's theorem, which is based on, Schur's theorem is like a mosquito. I'm smashing it with a sledgehammer here. Because what I'm using is the Jordan basis theorem. If we have the characteristic polynomial split, if you think about the eigenspaces, right, the generalized eigenspace with eigenvalue lambda, the dimension of it is the algebraic multiplicity. This is part of the Jordan discussion we had, right? So we know that the dimension of the block corresponding to the jth eigenvalue is m sub j by m sub j, right? So if you think about it, the matrix with respect to the Jordan basis is this, right? That's upper triangular because the Jordan, the non-zero stuff, if there is any, if it's not diagonalizable, it just puts 1 on the super diagonal. And if you take the direct sum of upper triangular matrices, you get an upper triangular matrix, all right? And as such, this is upper triangular, and then all we need to do is orthonormalize this. But if you think about how Gram-Schmidt works, if you feed k-chains to Gram-Schmidt, it's going to maintain the upper triangularity if you think about it. Think through this. If I do Gram-Schmidt, right, on the basis gamma tilde, like I'm going to start by just normalizing the first thing. Then I go to the second thing, and I just, if you look at how Gram-Schmidt works, it always builds the next vector just in terms of the vectors up to that point, which gives you the triangularity that you want. So that is my sketch of Schur's theorem proof, and I think that's enough for us. We just want to use it mostly. So definition. We defined this as in previous class as well. Okay, so we say a mapping is normal if tt star is equal to t star t, and likewise a matrix is normal if aa star is equal to a star a. Proposition: if you have a transformation is normal, then the matrix is also normal. So here's the proof of that. It basically rests on these two identities. The adjoint, the matrix of the adjoint is the adjoint of the matrix, and the matrix of a product is the product of the matrices composed. These things we know. So if you look at the product of the matrices T with T, you get the matrix of T with T star, if supposing that well, there's a star here, right? So And then if t is normal, I can trade that for t stars t, which then undoing what I just did gives me back to the matrix of t star matrix of t. Therefore, the matrix is normal. Yay. Great. Now, we have some examples of normal matrices. A rotation is normal. But you might remember this is our quintessential example of a not diagonalizable real transformation, right? Because we don't even have an eigenvector here in the real case, right? So normal doesn't necessarily imply diagonalizable in the real category. Something else we should notice, if we have either symmetric or anti-symmetric, we get normal. So both symmetric and anti-symmetric matrices are normal. So that's nice. These are the properties of normal transformations. Normal transformations preserve the norm. If t is normal, then t minus a constant multiple of the identity is normal. If you have eigenvalue lambda for t, then you have eigenvalue lambda bar for the adjoint of t. And finally, if you have distinct eigenvalues, then the eigenvectors are orthogonal. The proof of all of these things is very simple. For example, the length of t squared is t of x with t of x, which using the property definition of the adjoint, we move to t stars t acting on x. But normality gives me that's t star. Moving the t back, we got t star x, but that is the length of t star x squared. Consequently, we have that the length of t of x and the length of the adjoint of t acting on x are equal. The proof that t minus ci is normal is a straight calculation. I just multiplied it out, used normality of t, properties of the adjoint, and voila, normal. The proof that C, so you have u equals to t minus lambda I is normal by b, that's normal. And then if tx equals to lambda x for x not equal to 0, that means that ux equal to 0. So we have ux is equal to u star x by a, but that's equal to this, which gives me that t star x is equal to lambda star x. So we get that the adjoint has conjugate eigenvalue for the same eigenvector. They share the same eigenvectors, but different eigenvalues. The proof of orthogonality is simple as well. We start out with lambda times x1, x2, pull the lambda in, change it to a t, move it to the other side, gives it a t star. Then that's a lambda bar, 2, and then pull it back out. You got lambda 1 not equal to lambda 2 times something. The only way that can work is if the something's 0. So that's the orthogonality. This brings us to theorem 6.16, one of the major theorems of this section, namely that if we have a linear transformation on a finite dimensional complex inner product space, then T is normal if and only if there exists an orthonormal basis for V of eigenvectors. And the proof basically goes like this. You apply Schur's theorem. That gives you an orthonormal basis. Why can we apply Schur's theorem? Think about it. The characteristic equation is in the complexes, right? We're in a complex inner product space. Fundamental theorem of algebra says that any polynomial splits over the complex numbers. So Schur's theorem applies. We have an orthonormal basis. And as such, the matrix is upper triangular. Notice that the first vector is an eigenvector, yay. And then by induction, suppose that the first k minus 1 are eigenvectors of T. All right? They're orthonormal because we are using Schur's theorem. We already know orthonormal. And so if you think about it, if you look at the kth one, we have this in terms of by the upper triangularity, we have this formula. But if you take the inner product of that with Vj, you just get ajk. And but that is 0 because ajk is by definition, by our previous theorem about how to calculate the components, this, which is that, which is 0 because j is less than k here. So these are not the same. So then that means that tvk is akkvk, which is to say that vk is an eigenvector. The induction is done then. And so the theorem follows. Now the inverse direction, suppose T has, the converse direction rather, T has an orthonormal basis of eigenvectors, then that means that this is that, but aij is actually, each thing is an eigenvector, right? So the ijth component is lambda j times delta ij, it's a simple matter to prove that a matrix that has this formula satisfies the normal equations. You can easily check that if this is the formula for the matrix, then the normal equations follow. Yep.
Is being normal equivalent to having linearly independent columns?
It's more than that. Normal is a stronger condition than that. Because normality of the matrix implies that there exists an orthonormal eigenbasis. But we know lots of complex transformations don't have an orthonormal they don't have an eigenbasis, much less an orthonormal one. And I guess that's where we got to today. I'm pretty happy. So anyway, I'll shut up. I know you guys have apparently have other things to do than linear algebra. Go figure. I tell you.